as I'm sure you've already figured out, scientists like to use big words. So, next we're going to talk about massive stars and how their life cycle is different from that of average sized stars like our sun. So, let's see what happens when we look at a star much bigger than our sun. So, let's see how massive stars or bigger stars differ from uh, average sun-like stars. So not in the beginning. The beginning is fairly similar. Nebula, protostar, main sequence. When they go to main sequence stars, though, they are bluer and they burn through their fuel faster, so they'll only live 1 billion years or even less. Um, and that is because they are hotter, because there's more gravity, and then more gravity needs hotter fusion in order to balance it out. So they'll burn bluer because they are burning hotter, and they'll burn faster. So 1 billion, 10 billion, even longer years. Um, After the blue main sequence stars run out of fuel, they become red supergiants, very similar to red giants, just bigger. And that is again due to so much mass, they burn hotter, so they can fuse together more elements. So as you can see here, hydrogen, helium, carbon, but it can go beyond carbon. They can go beyond carbon, oxygen, neon, magnesium, silicon, and iron, and they fuse into these shells. Um, Iron is the last thing because iron cannot be fused together because it's so stable that even under those conditions with so much gravity pulling in and so much mass pulling in that they don't iron won't fuse together to make a heavier element. Um, so you can see a red supergiant size would take up a huge chunk of our solar system. So here goes the core, but the outer part of a red giant star goes all the way out, would go all the way out to almost Jupiter in our solar system. Lucky our star isn't that big. And again, that's because the core collapses, and then the fusion is so hot that it pushes out the outer layers, and the outer layers go further away. When they go further away, they cool down and they become red. An example of a red supergiant is Betelgeuse, because Betelgeuse is fun to say, and Betelgeuse is bigger than even Jupiter's orbit. Our sun is going to be itty bitty in there. And yes, I did say Betelgeuse 4 times just now. Um, Supernova is what happens next. So after um, all of these elements have fused together and created all this iron here, then the iron can't fuse together anymore, or the iron can't fuse together. So gravity takes over, and because there's no more fusion, and when there's no more fusion, boom, it explodes. Supernova. Um, the supernova, yeah, I said that already. Um, and then so the outer layers bounce off after they collapse back in, and that's your supernova. Now, here goes some pretty pictures of supernovae, because that's how the plural for supernova. That's just pretty. And that one too. And after all the debris clears away, you're left with a neutron star. And that is the next stage in neutron stars happen with stars that are 1.5 to about 3 times the mass of our sun. So things that are bigger but not much bigger. And because of the pressure from the explosion, we can get new elements. And so this is where we get things like gold and silver and uranium. Here on Earth is an ancient star that exploded billions of years ago, created heavy elements like gold. A neutron star, the gases from that supernova eventually used to make new stars and planets, which is like us. Um, what is a neutron star? Well, it's a bunch of neutrons. So that pressure or that explosion causes such a violent collapse that all that empty space in those atoms that we learned about in middle school gets pushed away, and you're left with this dense ball of just neutrons. So it has tons and tons of mass. It's super dense. So if we have Earth, white dwarf is about the same size of Earth, so this is the fate of our star. But then a neutron star is about the size of Chicago. So a really big city, but just the size of a city, but with way, way more mass than either of these two things combined. If you took a teaspoon of it, it would weigh as much as Mount Everest. Massive, larger stars, therefore, live fast and die young and die an explosive death, like a rock star. So this lady, Jocelyn Bell, detected radio pulses coming from space. They were nicknamed Little Green Men because they at first thought they were coming. The radio pulses were actually communication from extraterrestrials, but then they realized that they are pulsars. And pulsars are a type of neutron star that give off these radio pulses. And we'll listen to those in class. The stellar evolution of the most massive stars. So what happens with stars that are 3, 10, 20, much bigger than our sun? Well, they become really blue main sequence stars. So the beginning is the same. Nebula, protostar, main sequence star, but the main sequence stars are really blue. Because they are really hot, because they are really massive. And so then, after the supernova, the red supergiant supernova, they become black holes. And that is what happens to the core after the supernova and all the dust blows away. You're left with this black hole, and black holes are cool because nothing gets out of them, not even light. So it literally bends space and time and warps it so it's a different shape. That's how dense they are. They can, if they're in a binary system where there's two stars next to each other, they can suck in the star next to it, its sister star. Neutron stars can do this as well, and we can't see them directly. We can't see black holes directly, but we can see what they're doing. So we can see how they affect other things around them gravitationally, or even pulling in the mass. We can see X-ray jets being emitted from either side of them. Here goes a artist drawing. So you have the singularity in the middle. We have the event horizon where nothing else escapes. You have the accretion disk where everything's getting sucked in, and some of them we have a jet of X-rays coming out of the side. What do you think would happen if you fell into a black hole? It's interesting. First, the force of gravity would stretch and spaghettify you, which means that you would be pulled out into a almost infinitely long strand of atoms, one atom thick. So you would be stretched out until you became one atom thick, and however long that would be. Um, and the high energy electromagnetic radiation would burn the atoms that are left over from you. And after that, you would be crushed at the singularity to a single point. That's the name. Um, so the most massive stars live faster and die younger and die more explosive deaths. You can see a supermassive blue giant over here. So, in summation, the mass of a star determines if its life track. Stars much more massive than the sun leave behind neutron stars and black holes. Stars close to the size of our sun leave behind white dwarfs. Heavier elements, the really heavy elements, are made in supernovae and, um, sorry, uh, we're all made of the leftover stuff from when stars explode or stardust. See you next time. Hopefully, we shed just a little bit of light on the subject.